All right. Yeah, thanks everyone for being here today. My name is CoreyCaulkins. I'm a master's student in the GIST program here. And yeah, I'm presenting my master's project this morning, which is titled Supervised Classification of StinkNet in Maricopa County, Arizona. So go ahead and jump in. So a little bit of background. Stinknet is an invasive species here in Arizona. Originally, it's from South Africa, and it's actually classified as a noxious weed in the state since 2020, which is kind of like a higher classification of invasive species. Um, so it tends to kind of colonize areas that have been disturbed in the past. So that might be, post-fire environments. If there's been a fire recently, it's pretty good at coming in and colonizing transportation corridors, washes, those types of environments. But it's really a problem because it itself can lead to increased wildfire risk. As you can see in this image on the right side, it forms these really dense, large stands that then will dry out in the summer, and that can, add a lot of wildfire fuel that typically is not there, and also can just disrupt native plant communities. So it's something that we're worried about. It's become a larger issue over the last 10 or so years in Maricopa County. Just a couple more images. Yeah, like I said, it forms these very large patches that are almost hard to describe unless you see them with your own eyes. But so what do we do about it? Um, that's always evolving. I think this is probably the closest thing we have to kind of a typical workflow for addressing StinkNet. So, always it starts with surveying. We need to know where it is. And a lot of times that happens on the ground. So that might be a professional field crew that's sent out. That might be more of like a citizen science kind of situation. Um, but yeah, at the end of the day, we need to map it so we know where it is, so we know what needs to be mitigated. Um, Once we know where it is, either through mechanical means like pulling by hand or using tools, or if we have these really large dense patches, really chemical or herbicide means is the only way to effectively treat them. Um, but I'm kind of focusing on the first phase of this today, which is the survey. How do we find it? How do we map it? So obviously with a field crew on the ground, there can be some challenges with mapping StinkNet. Some areas might be difficult to access, or they might be dangerous to access. Um, Obviously, you're kind of limited by crew availability, or if you're relying on citizen science, that's something that's not necessarily within your control. Um, and finally, it can just be difficult to determine, which areas should be prioritized for removal efforts, especially when we're dealing with really large infestations like we're seeing in Maricopa County. Um, yeah, it can be challenging to kind of pinpoint, where we want to target exactly. So that's where remote sensing can help. Um, it might not necessarily replace ground surveys, but it can certainly augment them. So imagery can be collected through a variety of means. It might be a drone, might be a satellite, it might be an aircraft. But once we have imagery, we can use machine learning tools to basically to classify StinkNet remotely instead of or in addition to using crews on the ground. Um, and this is actually already being done in Maricopa County effectively. So this is a screenshot of a web map that Maricopa County has created. And they've actually been doing, so this on screen, this is Cave Creek Regional Park, but they've been doing this with all of the county parks, or at least these five that are listed on the bottom here. So they've been doing a drone-based classification annually since 2023 now. So essentially they use a drone to collect imagery in their park, and then use machine learning tools to analyze that imagery and find areas where they predict StinkNet is active. And so that's what the red is on this map. These are areas that have been classified as ThinkNet. And then that then can inform their treatment program afterwards. So really helps kind of pinpoint where the focus areas need to be in terms of StinkNet treatment. So drone imagery is great for classification. It tends to be higher resolution, which gives it more sensitivity to smaller patches of StinkNet. Again, it's great for accessing remote locations. Sometimes it might be more cost effective than sending out a ground crew. It also comes with a few disadvantages, though. Obviously, specialized equipment is required, training and licenses to fly drones. You'll only have data for areas that you've flown, which is a limitation. And then processing time and data storage can be a large burden with this type of imagery as well. So with that background, my study really looks at, is it possible to do the same kind of thing to map StinkNet remotely, but using publicly available aerial imagery rather than drone imagery? And in addition, which imagery source is better suited for accomplishing this? So I have two listed here. The first is NAPE for short, National Agriculture Imagery Program. This is a product collected by the USDA via aircraft, and it has full coverage over the entire United States, available to the public. And the second is PlanetScope imagery, which is collected by a private company called Planet via satellite. And so those are the two imagery sources that I wanted to look at and see if I could kind of reproduce the classification results that Maricopa County has produced. So these are my hypotheses for the project. These are null hypotheses. So first one, satellite and aircraft imagery-based classifications will not perform significantly better than random chance. That's the null hypothesis. And then the secondary one, there's no significant difference in the accuracy of StinkNet mapped using NAPE and PlanetScope imagery. It's the two imageries I just discussed. So those are kind of the default null hypotheses that we'll be evaluating. Okay, so moving into methodology, how we kind of approach this. So this is the study area for this project. You'll notice this looks like that viewer we were just viewing from Maricopa County. So this is actually the footprint of the drone imagery that Maricopa County used. So essentially I used that and then I overlaid it with this black is the park boundary. And I just kind of clipped those together to create this area in orange, which is the study area. So I wanted to make sure that we could do like a one-to-one comparison with what Maricopa County did and what I did. So yeah, just basically essentially reusing the same study area. So this is what the imagery itself looks like. So on the left is PlanetScope, which, as I mentioned, this is a satellite imagery product created by collected by the Planet company. It has a 3-meter spatial resolution, which means that each pixel in this image is a 3x3 ground area in real life, essentially. And it was collected in April 2023, which matches the timeline of the drone imagery that was used by Maricopa. And then on the right, we have the NAPE imagery, which is the aircraft collected USDA sourced imagery. It's higher resolution, so it's a typo. It's actually a 0.6 meter resolution, 60 centimeters. And then the other big difference is that it was actually collected in June rather than April. And so StinkNet is not at its peak flowering point in June. It's actually a little past it. So that's kind of a bigger difference between these two data sets is that, and you can kind of see it on the left, these large yellow areas, that's StinkNet, where it's not quite as easy to pick out on the right. And yeah, these are the collection means. So that's the satellite on the left and then the aircraft on the right that was used to collect these imagery sources. So in terms of the actual the machine learning part of this methodology, so this is the raw imagery that we're starting with, um, and essentially the training process. We have 5 predefined classes that we're attempting to train the model on. So we have stinknet, bare ground, other vegetation, roadways, and then brittle bush. And these were also borrowed from the Maricopa County methodology. Um, so essentially what I did is for each one of these classes, I created 20 to 30 training polygons on the map. So you can see them in this image here. Um, and basically this is to essentially teach the model like what each of these classes looks like in the imagery. Um, and then once those are collected, the model then takes those and kind of extrapolates those to the rest of the imagery. So it's using the classes that are human created to train itself and then to apply that to the rest of the imagery. So yeah, so that's what the whole process looks like. Um, I also just want to briefly mention that I did use 2 different classification models as well, or algorithms. Um, we don't need to get too in the weeds on it, but essentially, support vector machine is a process that um, basically is plotting all of the reflectance values and then trying to find the best dividing line between them. And it's using that. That's kind of the way it approaches classifying different pixels. Whereas random forest is a collection of decision trees that the model will create. And then they all essentially do like majority voting. And then whichever class most of them have decided is kind of the one that it classifies. So 2 slightly different algorithms. Both are pretty pretty popularly used in remote sensing. So I wanted to take a look at both of them and see how they both performed. Yeah, so taking those 2 things together, this is kind of what we end up with. So 4 different classifications were done. So obviously we have the NAPE imagery on the left, and then the 2 methods we just talked about, and then the PlanetScope imagery on the right with the same 2 methods. So this is just kind of a snippet of what each of them looked like, and you can see that they're similar, but there's definitely differences with each approach. So yeah, wanted to see which of these is going to give us the best results. So let's talk about results. So this is just an example of one of the classifications. The purple is the reference data from the drone imagery from Maricopa, and then the red is what I classified based on the aerial imagery that I had. And then this is a couple zoomed in areas. So you definitely see some correlation, also some areas where they don't overlap. Won't spend too much time on this, but these are the confusion matrices that I developed, which are basically just scorecards for how well each of the classifications did. And these let us kind of calculate some accuracy statistics. So I'll go ahead and just jump straight to those. And just a couple of note on the metrics we use. Precision and recall are kind of the 2 different ways of looking at accuracy. Precision is basically trying to figure out, of all the alarms raised, how many were real positives, and recall is looking at, of all the real positives that were out there, how many did we accurately find? And F1 score is essentially a weighted average of the 2. So that's kind of what we're going to use to judge the accuracy. So this is those accuracy values for each model plotted. Again, I don't want to get too into the weeds, but you can see on the top we have our 2 PlanetScope classifications. And then the white is the F1 score, which is kind of the combination of the precision and recall. So we can see that those 2 classifications were significantly more accurate in this metric than the 2 NAPE classifications. And yeah, these aren't obviously these aren't the highest values in the world, but we are dealing with a somewhat rare event. It's only about a 3.5% occurrence rate. So this is basically telling us that our classification model has significant prediction ability, above just like a random classification would. So going back to our hypotheses, based on this data, we can reject the first null hypothesis, and we can say that all the classifications did in fact have statistically significant prediction skill, which is good. That means that they're useful. And then our second hypothesis, null hypothesis, we can also reject. And we can say that PlanetScope actually did achieve significantly higher F1 scores than NAPE imagery did, which means that they had a slightly more accurate classification. So obviously there are limitations that come with this study. So we, typically with a classification, you're going out in the field and you're ground truthing. In this case, since we were looking at 2023 data, we were comparing to a previously classified reference data set. So there might be some, since we're not actually comparing to what's on the ground, there will be some accuracy loss there. As I mentioned, the two data sets we looked at were collected at different points in the season. So that could introduce some error as well. Ideally you'd look at two data sets that were collected on, the same day or the same time of year. This was just an RGB classification. I did not look at, any indices like NDVI or anything like that, but that might be a future direction that can be taken. And then the last note here is just that, for studies in advance, like I said, this was kind of looking at the past, but for studies in advance, Planet does offer some higher resolution imageries that can be scheduled. So that would be a potential future direction to maybe get a more accurate classification. All right, and I just want to say a special thanks to everyone who kind of supported me, mentored me, shared data with me. I really have appreciated it. And yeah, some references, but that's all I have. So I think we can move into Q&A.